All right, this video will have an example going over column buckling due to temperature changes, or what I'm calling thermal buckling. Um, and so here's the system. We just have, well, it just looks like a square shape right now, a square cross-sectional structural member with two fixed supports at the ends separated by 3 feet. And we're going to consider two different cross-section types. And we'll see why we choose these two in a second. But one is a square rod, so a solid square rod that is a 1/2 inch in both lengths, so it's a square. Also a square duct, so on both lengths it's 1.3 inches, and the inside is 1.2 inches. So the wall thickness here is, so it's 0.05 inches, 1/20th of an inch thickness. The material for both of them will be aluminum, so it has an elastic modulus of 10,000 ksi, a thermal expansion coefficient of 13 times 10 to the minus 6, 1 over degree Fahrenheit, and has a yield strength of 40 ksi. And what we need to do is determine for both cross-section types the temperature increase at which buckling will occur. So the first step here is to start calculating the important geometrical properties, but first let's just calculate the area, and then we'll see why these two shapes are interesting, these two cross-section types. For the solid rod, the area is just the length squared, which is 0.25 inches squared, and for the duct, which is hollow, chose it conveniently enough where the cross-sectional area, that the total amount of material here is the exact same for both. Okay, so they're both 0.25 inches squared. So we can take a column where the the area, the amount of material, is the same in two different cases, and see which one is going to be more prone to column buckling. So, and it being a temperature increase is interesting. You can think of a lot of cases where a square rod might have a temperature increase, in high temperature settings where it's not manufactured that way. Or it needs to be manufactured with that in mind. Or a square duct. So, that's maybe you have a duct in your house that has about this shape, and it's a pretty thick wall, and might, if it's a heating element, it might be exposed to some pretty high temperatures. Okay, so to get to our critical buckling load, which we need to look at, we need to know a few of these other quantities for the system. First of all, the elastic modulus is already given. We know it's aluminum, and it was given in the problem. But let's go to the first one, which is the moment of inertia. The moment of inertia, because it's a square, in both cases, this is going to be the same about both axes. So we don't need to consider a weak and a strong axis. There's only just, they're identical here. So for the rod, it's just 1/12 bh cubed. Since b and h are both the same, base and height, it's a square. That this is just that length to the fourth. Plug that in, and you get this quantity. If we do something similar for the square duct, where we take the outer moment of inertia minus the inner moment of inertia, we find that this one is much bigger. So this is 0.005, and this is 0.065. So considerably higher moment of inertia for the duct than the rod. So, and that's because, you should expect that. We have a lot more material further away from the axes. The amount of material is the same for both, but we have more of the material further away from the axes of rotation, or the axes of interest here. Okay, so then the next quantity here is the effective length factor. This is a fixed system. So our effective length factor is just a 1/2, and that's the same for both. Our length is the same for both too. It's 3 feet, which is in inches is 36 inches. So if we plug all that in, we find that the critical load for the rod is 1.58 kilopounds, and the critical load for the duct is 19.8 kilopounds. And again, the only thing that changes here is this moment of inertia. And with the moment of inertia being much bigger for the duct, we should expect that the critical load be much higher for the duct, which means that the buckling, the rod is much more prone to buckling than the duct is. Okay, so then to compare it to the temperature associated with this critical buckling load, we need to recall that our total axial deformation has the internal force part plus the thermal deformation. And with a doubly fixed support, doubly fixed rod or duct in this case, that total deformation is fixed at 0. There can't be any deformation. So we just plug in 0 for the deformation, and we see that, we know the length, we know the area and the elastic modulus, we know the thermal coefficient, expansion coefficient from given in the problem statement, and we know the length. So with that, we can solve for the temperature change in terms of the internal force, and then just known quantities. And at the critical buckling load, this internal force is just minus it's just the negative of the critical load. And that's because the critical load, it's a compressive load, but we define it as a positive quantity. So the internal force is in compression, but P critical is just given as a positive quantity. With that, we can now plug this in for our two different loads. And for the rod, buckling could occur at a temperature increase of just under 50 degrees, which is a large temperature increase, but not impossible or not unrealistic. The critical temperature change for the duct with the much higher critical load is a much higher temperature change, which is 611 degrees Fahrenheit, which is now we're talking a little bit unreasonable of a duct buckling, of buckling for the duct, because that temperature change is quite extreme. But you could come up with situations where that could occur. Let's see here. So, we see that the rod and the configuration of the same amount of material being in a square shape as opposed to a hollow square shape has a much lower critical load and therefore a much lower temperature change. But we do have this yield strength too. So let's compare this to the possible yielding of both columns. Yielding is going to occur for the material at 40 ksi, a stress of 40 ksi. And here we're interpreting this as a compressive stress. And so this is associated for our material, or for our columns here, when the load, our yielding load here, is just the yield strength times the area. Area is the same for both. So for both the rod and the duct, this could occur, the yielding will occur at 10 kilopounds. Well, we compare this 10 kilopounds to the critical buckling load for the rod. So as we increase the load, as the temperature increases, and therefore the internal load is increasing, the internal force is increasing, this will be achieved first, right? You're going to get to 1.6 kilopounds before you get to 10 kilopounds. So therefore the rod will buckle before it yields, and it's going to occur at this 48.8 degrees Fahrenheit. But the duct, if we compare the 10 kilopounds to its critical buckling load of 19.9 kilopounds, actually it's going to yield before it buckles. Right? So as we increase the load, we're going to hit 10 before we hit 19.8. And so therefore, we can find the temperature change at which that occurs just by plugging it into the same formula, the 10 kilopounds. And we find that that's going to occur at a temperature change of 308 degrees Fahrenheit. So the net result here is the duct, this is still pretty large, so but not impossible, to go from freezing water to boiling water. It's about on the same order here, so it wouldn't be unheard of, but I don't know. Overall, we say the duct under realistic conditions, or just not extreme conditions, that the duct is not really at risk of failure to either buckling or compressive yielding. But if it did fail first, it's going to yield before it buckles. Whereas the rod is going to buckle before it yields, and at, I don't know, put this in quotes, moderately large delta T's 50 degrees. It's all relative to what we're talking, but the rod's going to buckle at about 50 degrees Fahrenheit temperature change. So it depends on what we're subjecting these columns to, but the rod will definitely be more at risk to failure. So the cross-sectional shape is important, and this one is more prone to failing than the duct shape.